All right. So I apologize for not being able to be here today, but I thought what I would do is go through this presentation on solving problems using Newton's laws that I've adapted a little bit so that you just have the absolute most important information. Then you have a few practice problems to do with walked through solutions. Normally, where this would come, we would have it happening after we'd done some good demonstrations to show Newton's first and Newton's second law. Uh, but I will trust that you've had some experience with F is equal to ma, at least enough to understand that F equals ma stands for the net force is equal to the mass times the acceleration. And that, along with free body diagrams, will give you enough to solve these problems, even if you aren't fully convinced that that's true. The best way to go through this video is to watch the introduction through the sled problem, then to pause as I show you the different problems so that you can try to work them on your own. And then you can either quickly look at the solution to see if you've done it correctly, or if you're having trouble with a problem, you can watch through the solution and I'll explain it to you. So this will end up being kind of long, but you may end up not watching most of it. So that'll be great. The goal with this lesson is to help you use Newton's second law quantitatively and qualitatively. These other pieces we're not going to get to as much. Newton's laws, they're usually thought of as being three of them. There are technically, I suppose, four of them. And really, there's only two of them that are particularly important. So most people don't have this zeroth of Newton's laws, which says that mass is conserved. All of Newton's laws assume that you have a constant mass for objects. So the masses of objects can't change. And as long as that is true, then an object will continue in its state of rest or uniform straight line motion unless acted upon by a net force. In other words, what we mean is when there is no total force acting on an object, it will stay at rest or it will stay moving at a constant velocity. That law is actually contained in the most famous of Newton's laws, Newton's second law, which says that the acceleration of an object will be proportional to the net force and inversely proportional to the mass. More often written as F is equal to ma, but I like this form because it feels causal to me. The acceleration is caused by the net force. And that contains the first law because if the net force is zero, then the acceleration will be zero, which means that the object will stay at rest or in constant straight line motion. The final of Newton's third laws, which isn't going to come up much today, is that all forces come in pairs, meaning that when one object pushes against another or pulls against another, then that object pushes or pulls back. For example, if you have a person standing on the floor and the normal force pushes upwards on their feet, there's an equal and opposite force that the feet exert on the ground, pushing down. So more directly, when object A exerts a force on object B exerts an equal and opposite force on object A. So what are Newton's laws problems? Well, the challenge with this, and hence the sad face, is that Newton's laws problems can really be anything. They can involve one object, more than one object. They can be problems that are in one or two or even three dimensions. They can be objects that are at rest, moving at a constant velocity or accelerating. And they can have forces that are all known or some forces are unknown. So really anything can be a Newton's law problem. So there's a lot of different situations. There are some new techniques, particularly those free body diagrams are particularly helpful. There are easy mistakes to make. If you miss some of the forces that are involved, you can run into trouble. If you have difficulty with vector addition techniques, you can run into trouble. On the plus side, accelerations are really related to net forces, and so there's really only one equation that we work with here, which is F is equal to ma. There's some small other things, but we don't have to pick between four different Suvod equations when we're working with Newton's laws problems. The mathematics that we'll see when it becomes a little trickier involves systems of equations, where you have multiple equations that relate to the same two or possibly three variables, and you can use techniques to solve for each of them. So that's going to be something that you'll brush up on. The approach that we're going to take to problem solving here, and you'll see this in a couple of examples, is we're going to start with a sketch of the situation where we draw things, right? Where we take a look at what we see here, and then we'll label the forces, the angles. You want a picture to be working with. Then you'll want to make a free body diagram for each object of interest. In our case, for today, we're only going to be looking at individual objects, so we just have one object involved. And when we make our free body diagram for that one object, we'll want to try to make the magnitudes and angles as accurate as possible, or at least estimate them, so that the picture is as helpful as it can be. We'll make it large so that we have space on the paper to make some annotations. And we'll label the forces, including values, if possible. Next, we'll resolve forces into components. And finally, we'll apply Newton's second law along each direction. So just like with kinematics, where we could look at vertical and horizontal separately, with dynamics, we'll look at horizontal and vertical separately, because that assumption that motion along the vertical direction doesn't affect motion along the horizontal direction remains an assumption that we make here, and it is proven to be true over and over again. Some quick illustrations, and you can work along with this and maybe pause, is what do we look at if we have a 20 kilogram box at rest on a table? Well, your free body diagram, which should be very quick to draw, is going to involve two forces, one that points up and one that points down. The upward force will be the normal force on the box from the table, and the downward force will be the force of gravity, labeled probably with a G and an N. And then we can calculate the weight of the box, which would be the acceleration due to gravity times that mass of 20 kilograms. We'll usually estimate G as 10 for work that we're doing quickly, so you have 200 newtons down. And you don't know what the normal force is. However, we do know that the acceleration of the box is 0 because it remains at rest. And so the upward force on it has to be 200 newtons so that the total force is equal to 0. So your final free body diagram would involve an upward arrow, normal force of 200 newtons, and a downward force of 200 newtons from force of gravity. That would give you an acceleration of 0. I'm going to skip over this picture involving two different objects and move over to the first example problem here, which you should watch through, which is looking at a statics situation. So statics problems are maybe the Newton's first law problems, where the objects are remaining in constant motion. In this case, we have a 45 kilogram child being pulled along at a constant speed by a researcher, being very safe in her helmet. She's exerting a 250 Newton force at an angle of 37 degrees on the string. Find the value of all the other forces. So here you can see the drawing is already on the screen. We have a picture with the child and the researcher and the rope, and we've even constructed a little bit of a simple free body diagram right on top of the child. But of course, having the picture of the kid, picture of the researcher, and the rope and things drawn in there, it's not going to be an isolated free body diagram. So the first step that we'll use as we work on this problem is to actually draw a free body diagram. So I've put my dot. I've done a little bit of a pair of vertical and horizontal axes. And now I've added the four different forces here. Now, how have I chosen to draw the size of these forces? Well, I've drawn the tension force first, and I'm thinking about that as having a magnitude of about 250 newtons. And I'm guessing the force of friction is going to be similar because the child is moving at a constant speed. I expect the force of gravity is going to be larger because I estimate in my head that that's going to be about 450 newtons. So I draw that downward and longer. And the normal force is going to have to point upward, but it's probably going to be a little smaller than the force of gravity because there's an upward force from the string also. I think I'm going to need to move my face just a little bit. The next step here is to start labeling in some things that I know. I label the value of that 250 Newton force and 450 Newton force from gravity because I can calculate them. And then I'll add in that 37-degree angle. So I'm starting to put some numbers in there because they're numbers that I know from the problem. The 250 newtons is there directly, and the 450 newtons I calculate from 45 times g, or I'm going to use and estimate it with 10, just to make the numbers feel a little simpler. Next piece is I want to resolve those vectors into components. I'm going to do that right on the free body diagram just to prevent there being any confusion. I'm going to draw them as dotted lines so that I know that those are components of the 250 Newton force, not other forces. The horizontal component will be the tension times the cosine of 37, and the vertical component will be the tension times the sine of 37. I remember that 37 degrees is that special angle with a 3, 4, 5 right triangle. So 5 times 50 newtons, 4 times 50 newtons, and 3 times 50 newtons gives me an upward force of 150 newtons and a rightwards force of 200 newtons. Still nothing about the normal and frictional force, but the next step is to think about Newton's second law. Newton's second law tells us that because this is at a constant speed, the acceleration is zero, and therefore the net force has to be zero. The net force has to be zero both horizontally and vertically. So when I look at the sum of all the horizontal forces using the sigma notation for the sum and FH to represent the horizontal forces, the sum of the horizontal forces has to be zero. With 200 newtons pointing to the right and a frictional force pointing to the left, those are the two forces that are acting horizontally. They add up to zero. And so the force of friction has to be negative 200 newtons. That negative is telling us that we drew friction correctly. It points to the left. And the magnitude is the same as the magnitude of the horizontal tension. Some people might write the sum of the horizontal forces as zero and write 200 newtons minus the force of friction because they see the arrow pointing the other way. Then you would get the force of friction is equal to 200 newtons with a positive, and that's okay too. A third way of doing it would be to say the forces that point to the right have to be equal to the forces to the left. And so you could say that the rightward force of 200 newtons means that the frictional force has to be 200 newtons to the left. Lots of different ways of applying that really it's Newton's first law here to find that the frictional force is 200 newtons. And then next, we do this with the vertical forces. The sum of the vertical forces is equal to zero. Here we have three forces because I have gravity, the normal force, and the vertical force associated with tension. I use the negative 450 newtons for gravity, positive 250 newtons for, mistake. I have made that mistake in several places, so I'll have to fix that on the fly. Positive 150 newtons here. And so the normal force would then have to make up the difference of 300 newtons. So there's a typo here. This is not 200 newtons. It should be 300 newtons upward. We're going to come back to this problem, so that's going to come back again. Sorry about that. At this point, we've solved for all the forces. We have our 250 Newton force of tension, 150 newtons up, 200 to the right. Gravity, 450 newtons down. We could get that directly from the problem. The force of friction, 200 newtons to the left from Newton's first law horizontally, and 300 newtons for the normal force upwards associated with the Newton's first law for vertical. Here are two other statics problems. These are commonly called, like, say, sign problems, S-I-G-N, because they involve the hanging of a sign for display. The first one involves a 10 Newton weight sign. So the force of gravity is 10 newtons on the side, and two strings with tensions that have an angle of 45 degrees and 30 degrees with the horizontal. The question is to find the tension in those two cables so that the sign doesn't fall or doesn't rise. We have a second version of this problem where there's a weight W pulling down on a string, creating tension 3, and a horizontal string and a string at an angle of 60 degrees with tension 2 and tension 1. And the question is to find the tension in each cable. I'll go through solutions in just a moment. You should try drawing the free body diagram, labeling the values of the forces that you know or their components, and then working with Newton's first law that the sum of the forces has to be 0, both horizontally and vertically. Okay. I'm trusting that you have now worked or attempted to work these problems, or at least gotten stuck drawing the free body diagram and labeling it. I'm going to go through solutions now. So for the first one, when we draw the free body diagram, we have tension 1, tension 2, and the downward tension. Oops, looks like I have another mistake here. In my solutions, I said that this was 100 newtons down. It looks like I made the mistake of assuming that this was a 10 kilogram sign instead of a 10 Newton sign. So my numbers are going to be off by a factor of 10 as I go through the problem. Because it's in equilibrium, we know there's no acceleration. We can't break these forces really into components because we don't have the values of T1 and T2. So I'm just going to have to write that the leftward and rightward forces are balanced. So T1 times the cosine of 45, the leftward component, has got to be equal to T2 times the cosine of 30 for the rightward component. And this gives me an equation. T2 is equal to T1 times 0.82. That 0.82 being the cosine of 45 divided by the cosine of 30, which is going to be like the square root of 2/3, I'm guessing. And that's one equation, but we can't make any progress on it. When I look vertically, I have 100 newtons down and the two vertical components of tension pointing up. So the 100 newtons down is equal to T1 times the sine of 45 plus T2 times the sine of 30. Substituting in for T2 is equal to T1 times 0.82, I get that the 100 newtons is equal to 0.71, that's the sine of 45, times T1, plus 0.82 times T1, that's the same thing as T2 from the first equation, and then the sine of 30 is a half. And I can go on to solve for the value of T1 is 89 newtons, and then 82% of that is T2 at 73 newtons. Of course, if you used the 10 newtons, you would have come up with 8.9 and 7.3. With the next solution, let's see if I don't make any mistakes here. There's no numbers, so that usually helps. So we have the free body diagram drawn here, T2 to the left, T1 up and to the right, T3 down. And the only thing we know is that we'll say T3 is equal to the weight of this object. So again, horizontally, we can't actually find the horizontal component here, but we know it's equal to T1 times the cosine of 60, and that must balance T2, which is pointing horizontally to the left. So T1 cosine 60 is equal to T2, or T2 is equal to a half of T1 because the cosine of 60 is a half. Vertically, we have T1 times the sine of 60. The vertical component has to be equal to the weight so that these are balanced and there's no acceleration vertically, which gives us a second equation that T1 is equal to 1.15 times the weight. And since we know that half of T1 is T2, T2 is 0.58 times the weight. Here's another situation that we commonly see that involves an object that is linearly accelerating. In this case, it's not a static situation, it's a dynamic situation where an acceleration is possible. So, in the cases where the object is accelerating, in this case, a person, the Newton's second law is what we'll need to use that tells us that the acceleration is equal to the net force divided by the mass. In order to understand these problems, we have to understand how a scale works. Scales are interesting because we use them to find our mass. Most of the time, the scale that you would stand on will tell you what your mass in kilograms is. However, what they actually measure is the normal force that the ground is pushing up on your feet with. In this way, when your normal force changes, the scale will read something other than your mass. If you get onto a bathroom scale and you look at measuring your mass and you sort of bob up and down, what you will see is that the force or the mass that it reads goes up and down as well. In order to get it to be correct, you have to be standing still. So we have a special scale in here that instead of reading in kilograms, reads in newtons. It reads your actual normal force on the ground. And when you're going to do is you're going to bring this into your elevator. We may do this as a demo at some point. You can certainly do it in the elevator in your own building if you don't mind embarrassing yourself when you arrive at the ground floor. And we're going to take this man, mass of 70 kilograms, standing on the floor in the elevator on a scale. Find the normal force he experiences from the elevator floor when the elevator is standing still, moving up at a constant speed of 3 meters per second, moving up with an acceleration of 4 meters per second squared, moving down with an acceleration of 4 meters per second squared, or moving down but slowing down to a stop with a deceleration of 4 meters per second squared. Again, start with a free body diagram, label any values that you know, and in this case, you may need to have a situation where acceleration is involved and the net force won't be zero, but it will be equal to the sum of the vertical forces. I'll go ahead and let you try some of these, then move on to the next slide where I'll do answers to them. You should pause and do those. Here's our solutions. So in situation A, standing still, the free body diagram has the weight down of 700 newtons and a normal force upward. Because the acceleration is zero, this is a Newton's first law problem, a statics problem, and so the normal force has to balance the force of gravity and will be 700 newtons. The same thing happens in situation B. When you're moving up at a constant speed of 3 meters per second, that's also Newton's first law. The same free body diagram. In this case, the normal force will be the same as the weight because, again, the acceleration is equal to zero. Even though the person is in motion, the net force is zero and there's no acceleration. C brings us into a situation with an acceleration. The normal force still points upward and the weight still downward with 700 newtons, but because the acceleration is upwards, the net force has to be upwards. And the magnitude of the net force is equal to 70 kilograms times the 4 meters per second squared upward. And so the net force is going to be the normal force up minus the weight, or 700 newtons. So this is the total force. And that's going to be equal to the mass times the acceleration. Substituting in 700 newtons for the weight, you can find the normal force is 980 newtons. And you can feel this when you get into an elevator and it starts moving upwards. You'll feel momentarily like the bags in your hand have to be pulled up a little bit more. Your feet feel like they're being pushed against and you feel a little bit heavier. If you were standing on a scale, the value would read a bit higher. In situation D, the acceleration is downward. So in this free body diagram, the same net force, but in this case, it leads to an acceleration of 4 meters per second squared downward. I'm going to keep that to be my positive direction so that when I do mass times acceleration, it's 70 times 4 downward. But now I'm going to change so the net force shows the weight downward and the normal force in the upward. But now the weight is positive and the normal force is negative. Of course, you could equally write this equation as normal force minus weight is equal to 70 times negative 4 meters per second squared. Either way, the opposite happens from situation C. The normal force is a little bit smaller as you accelerate downward. This is what happens to you when you are on the top floor of a building and the elevator starts to move down. There's this moment where you feel a little bit lighter and you lift up. And so your normal force is a little bit smaller. Situation E, moving down and slowing down with a deceleration. Moving down and slowing down. If you are moving downward but going slower, your acceleration actually points upward. So this situation ends up being the same as situation C. Make sure you can understand why that's true. And maybe think about what's the situation that's the same as D. When we look at friction, and we'll talk a lot about this picture later, we see that there are two different types of friction. There is static friction, which is an adaptive force, and there's dynamic or kinetic friction, which it gives a constant force. It turns out that that force of friction, your dynamic friction, is proportional to the normal force. And there's a value called the coefficient of kinetic friction that gives the constant of proportionality. It's a number that is almost always less than 1, and it tells you what percent of the normal force is the force of kinetic friction. So we'll use frequently the kinetic friction is equal to, it should be here, but I didn't write it, is equal to mu k, sometimes written as mu d for dynamic friction, times the normal force. So for example, if you have a wood-on-wood contact and those are sliding against each other, the coefficient of kinetic friction is 0.2, which tells us that the force of dynamic friction will be 0.2 times whatever the normal force is. If the normal force, for example, with our man standing in the elevator is 700 newtons, then the force of kinetic friction, if he were sliding across the floor, would be equal to 0.2 times 700 newtons, or 140 newtons. The steel-on-steel contact has a larger coefficient of friction, which means that if you have steel-steel surface contact, you're going to have a larger amount of friction. And if you have, for example, joints that are lubricated or joints that are in human limbs, those values can be quite low so that large amounts of normal force don't give very much friction at all. Static friction, on the other hand, is an adaptive force, and it's as large as it needs to be to keep the objects at rest. However, it does have a maximum value equal to a coefficient of static friction times the normal force. It's important to realize that the static friction doesn't always have this maximum value. It changes equal to an applied force on the object. You can think about this if you're looking at your computer, and if you push on your computer and it doesn't move, you know that the force of friction has to be exactly balancing out the applied force from your hands. But if you push too hard, your computer will start to move. And you know that you've exerted a force that is larger than the maximum force of static friction, and the type of friction that you have becomes kinetic friction. So what this diagram is showing is that as you apply a larger and larger force to an object, the force of friction initially changes as there is no motion between the surfaces. And as the force gets larger and larger, you might eventually reach the maximum value of the force of static friction, mu s times the normal force, at which point the friction changes to kinetic friction. The fact that this little drop happens is because of a very common feature of friction coefficients, which is seen in this table. The coefficient of static friction is almost always significantly larger than the coefficient of dynamic friction. We can see that in certain situations where we want very little friction, Teflon being a wonderful material that has low friction, and of course, human joints, these numbers can be very close together, but usually there's a drop when you get to kinetic friction. So here's a question. Can you sketch this graph, but add the numbers correctly for a 10 kilogram steel block being pushed across a steel table? The drawing will be basically the same, but see if you can get the numbers correct. You should do this now, then I'll show a solution. Here we have the example. You can see that the drawing is the same. The force of friction, the force applied. You have the static friction section, and then the dynamic friction section. To find the values on the axes, we look at steel on steel with an unlubricated surface. And a 10 kilogram steel block means that there's an upwards normal force of 100 newtons to balance the 100 Newton force of gravity. The kinetic friction is easy to do. We find that the kinetic friction coefficient is 0.6. So the force of kinetic friction will be 60 newtons. And the coefficient of static friction gives the maximum amount of static friction as 0.7 times the normal force, or 70 newtons. So in the first part of the graph, between 0 and 70 newtons of applied force, we have a proportional force, or actually it's a proportion of 1. The same force applied as the force of friction until we reach 70 newtons, at which point the object begins to move and the force of friction becomes the kinetic friction, which is constant at 60 newtons. Let's revisit the friction sled problem with 3 different levels of dynamics problems. So go ahead and you can pause. I'll go through the solutions one at a time. You can read these questions. Level 1 should feel quite easy. I would expect that you would be able to do this from the example we did before, and the idea that the coefficient of friction is what you're trying to solve for, that the force of friction is proportional to the normal force. Level 2 becomes a little bit harder because we look at first static friction to figure out how hard the researcher has to pull, and then dynamic friction once the sled starts to move. Level 3 is actually very difficult beyond the scope of this class, but for those of you that want a challenge, it may be worth looking at. Let me go through. I need to go quickly because the next class is about to start. Here's the friction sled. I've included the problem from before because, of course, you need to know what the values of the forces are in order to find the coefficient. Unfortunately, this has the same mistake that I made before. The normal force should be 300 newtons. So when I've calculated this incorrectly, my number comes out to be wrong in this picture. But the upward force, remember, the normal force is 300 newtons. In this case, because the force of friction is 200 newtons and the normal force is 300 newtons, we can find the coefficient of friction will be 0.67 because the frictional force is 66% of the normal force. Okay, so that was a pretty straightforward one. The next one I hope I've done correctly. Let's see. It says, suppose the coefficient of dynamic friction is 0.6 and the coefficient of static friction is 0.75. Find the minimum force at 37 degrees to start the child moving. In this case, we'll start with the static diagram. We have the force that is being applied, which is now unknown, has 2 components. Fortunately, that 37 degrees, the 3, 4, 5 triangle, means that the horizontal component is 80% of that applied force, and the vertical component is 60% of that applied force. The force of friction is found from the normal force. It's 0.75 times the normal force. Since we're in a static situation, we're going to look at the way that this balances out. Vertically, the normal force has got to, added to the upwards force from tension, has to balance out the 450 newtons down, the force of gravity. So we have one equation, the normal force is equal to 450 minus 0.6 times the force applied. And then horizontally, we know that at a rest, 0.75 times the normal force worth of friction is going to be equal to 0.8 times the force applied. That component, that's the horizontal component of the applied force. Rearranging that, we get the normal force is 1.07 times the applied force. Now we can make that substitution into our first equation to solve for the applied force. And rearranging it, we can find that the applied force is 270 newtons. Once the child starts moving, if we have that same 270 Newton force, we can now calculate what the two components are. The situation changes, though, because we don't have 0.75 times the normal force for static friction. We have 0.6 times the normal force for dynamic friction. And so now we don't have balanced forces horizontally. We do have, we can find the normal force. 450 down, 162 up means the normal force has to be 288. The force of friction at 0.6 times the normal force can then be calculated as 173 newtons. And so the net force vertically is equal to 0, but horizontally we have 215 newtons to the right, 173 newtons to the left. So we have a net force of 42 newtons, and we can then calculate the acceleration with Newton's second law, the net force divided by the mass, or 0.93 meters per second squared. And finally, the problem that we know goes beyond what we're expected to do. How can you, obviously pulling at a different angle trades horizontal force for upward force. How could this affect the acceleration of the child? What's the optimum angle for somebody to pull? Here, this problem becomes challenging because the vertical and horizontal components will now depend on the angle, which is the sort of independent variable, or the variable that we're trying to optimize. But we're still going to know that vertically we have a static situation, normal force plus the force, the applied force times the sine of theta must balance the force of gravity. And horizontally, the F cosine theta is going to be equal to mu times the normal force. We can then come up with a complicated expression for the acceleration. The net force will be F cosine of theta minus the force of friction. The force of friction is mu times the normal force, which we can find from the vertical force. So we have F cosine of theta minus mu times mg minus F sine of theta over m. What we're going to do is we're going to try to optimize this. And in order to do that, we'll assume that there's no acceleration, and we'll find the value that gives the largest, or where the force can be the smallest. You rearrange here, and you get an expression that depends on theta. And here you see a link to a Desmos that shows what that looks like. Again, this goes outside of what you'd be able to do, so I just wanted to give you a little something to think about if you wanted to extend. I'll suggest a few problems for you to work on, to do problems like this for homework, and I will see you soon to finish up with this. I guess that's going to be Tuesday. Have a great weekend.